When you look at a modern CAD model or a finalized engineering blueprint, there is this distinct illusion of absolute rigid perfection.
Oh, yeah, totally.
I mean, you see these mathematically flawless lines defining an object in this pristine digital void. And the dimensions, they just seem binary. Like a machine shaft is 1 inch in diameter or it's not.
Right.
The hole is ½ inch from the edge or it's not. It is a really comforting idea that the physical infrastructure of our world, the engines, aerospace components, medical devices, are born from that kind of flawless mathematical certainty.
It is an appealing illusion for sure. We engineer these complex assemblies expecting them to operate flawlessly, so naturally you assume they are manufactured to a state of absolute theoretical perfection.
But the moment you step off that digital screen and onto an actual factory floor to cut metal or mold real polymer, that illusion just shatters completely.
Oh, instantly. You are suddenly dealing with tool wear, thermal expansion.
Machine vibration.
Yeah, machine vibration, material inconsistencies. The physical world is entirely imperfect.
And today, we are doing a deep dive into a document that tackles that exact reality head-on. We are pulling from this incredibly dense engineering text. It's called Engineering and Design-Geometric Dimensioning and Tolerancing.
Which, honestly, to the uninitiated, looks like a cryptic collection of symbols, boxes, and crosshairs just scattered across a drawing.
Yeah, it looks like alien math. But our mission today, for you listening, is to decode this specific blueprint language.
Right.
Because what this source document reveals is that GD&T, geometric dimensioning and tolerancing, isn't just a drafting standard. It is this massive hidden financial superpower.
It really is.
It's an engineered philosophy that drastically reduces manufacturing costs, simplifies complex inspection procedures, and serves as the literal backbone ensuring every mass-produced physical object you interact with actually fits together. So, okay, let's unpack this.
Let's do it.
To understand the shift GD&T represents, we really need to look at the incredibly expensive problem it was trying to solve. Because the global supply chain didn't always operate with this standardized language, right?
No, not at all. The standard actually has its roots in the late 1930s. There's a man named Stanley Parker.
In Scotland.
Yeah, he worked in a torpedo factory in Scotland. He is widely credited with introducing the foundational concepts. But the system didn't gain widespread global traction simply because someone had a good idea.
Right. Things never do.
Exactly.
Yeah.
It required a massive logistical crisis to force the industry's hand, and that crisis was World War II.
The scale of World War II production just fundamentally broke the old system of manufacturing.
Completely broke it.
Because before the war, a company building a complex machine likely handled a vast majority of that production entirely in-house. Like the design engineer could literally walk down to the foundry or the machine shop.
Yeah, they were right down the hall.
Right. So if a traditional coordinate drawing was a bit vague about how to measure a specific feature, the designer and the machinist just had a quick conversation. The design intent lived in the minds of the people making it, rather than being, explicitly encoded on the paper.
And suddenly, wartime production volumes made that localized approach impossible.
They had to outsource everything.
Exactly. Companies were forced into decentralized manufacturing. They were farming out sub-assemblies to hundreds of different shops across the country and eventually the world.
Wow.
So the machinist cutting the metal was no longer in the same building or even the same time zone as the engineer who designed it.
So the new manufacturer had to interpret a traditional coordinate drawing entirely on their own.
Which exposed the inherent flaws of those traditional drawings.
Yeah, and the source material has a brilliant visual comparison detailing this exact breakdown. It shows an old-style coordinate drawing, it's figure 5.1 in the text, and then the exact same part drawn using modern GD&T.
Right, the stepped shaft example.
Yeah, the part is a stepped shaft. It has a narrower section that is 1.000 inch in diameter and a wider section that is 2.00 inches in diameter. The old drawing simply draws a single center line running through the middle of both sections.
And it instructs the machinist to drill a hole exactly ½ inch from that center line.
Which seems fine, right? If I have a drawing, shouldn't a ruler be enough? Why is a center line ambiguous? It's like a recipe saying, bake until done without a temperature.
What's fascinating here is that the center line is an entirely theoretical concept when you are dealing with physical reality.
How so?
Well, in a CAD program, the 1.00-inch cylinder and the 2.00-inch cylinder are perfectly coaxial. They share a flawless, mathematically identical axis.
Right.
But when a physical lathe turns that piece of steel, there will always be some slight run out or offset.
Ah, I see.
The two cylinders will never share an absolutely perfect, identical center line in physical space.
So the machinist looking at that old drawing has to make an arbitrary choice. The drawing says to measure half an inch from the center line to drill the hole, but because the two sections of the shaft are slightly eccentric, the center line of the 1-inch section is in a physically different location than the center line of the 2-inch section.
Right.
So if one machine shop uses the 1-inch section to establish their 0 point, and another shop uses the 2-inch section, they are going to drill that hole in two completely different locations.
And that is exactly what happened.
Oh, man.
Manufacturers were guessing based on arbitrary features, often establishing their measurements from surfaces that had absolutely nothing to do with how the part actually functioned in the final assembly.
So they would drill the hole, the part would pass their internal inspection based on their guess,
Yeah.
and they would ship it.
Yep. But when that shaft arrived at the main assembly plant, the hole wouldn't align with the mating component.
It wouldn't fit. So you end up with massive scrap rates, totally wasted machining time, and bottlenecks in critical production. All because the traditional drawing was functionally ambiguous.
GD&T was the structural solution to that ambiguity. It replaced implicit assumptions with explicit, universal instructions.
No more guessing.
Right. The designer uses specific symbols to clearly dictate not just the size of the features, but exactly how they relate to one another functionally. It completely eliminates interpretation on the shop floor.
But to eliminate that interpretation, you need a universal starting point.
Yeah.
Right? A 0 point that everyone, the designer, the machinist, the quality inspector, agrees is the absolute foundation of the part.
Yes. In the text, this is defined as the datum reference frame.
Right.
The datum reference frame solves the centerline ambiguity by establishing physical reality. To manufacture or inspect a part repeatably, you construct 3 mutually perpendicular planes.
And the text notes, this is basically based on the Cartesian coordinate system René Descartes invented, which is pretty cool.
Yeah, it maps the part into a pristine 3D coordinate system. These planes are exactly 90 degrees to one another.
But wait, we just established that the manufactured part itself is imperfect.
Yeah.
It has form variations, bows, surface irregularities. You can't use an imperfect warped surface as your perfect 0 point.
No, you can't. So the GD&T system relies on datum simulators.
Right, these are pieces of precision manufacturing equipment, like a high-grade granite surface plate or a calibrated 3-jaw chuck.
Exactly. The simulators act as the physical manifestation of those perfect geometric planes. And the rules for how the imperfect part interacts with those perfect simulators are strictly defined by degrees of freedom.
Which is how it moves in space.
Right. Any object in 3D space has 6 degrees of freedom. It can translate along the X, Y, and Z axes, and it can rotate around those axes, pitch, yaw, and roll.
Got it.
The goal of the datum reference frame is to arrest those degrees of freedom so the part is locked in a singular, repeatable position.
And the standard dictates a 3-2-1 point contact rule for this. I want to make sure I understand this. Your primary datum feature requires a minimum of 3 points of contact on the simulator.
Yes.
That arrests 3 degrees of freedom. It stops the part from moving up and down in the Z-axis, and it stops it from rotating in pitch and roll. It establishes a solid base.
Spot on. Then, your secondary datum feature requires 2 points of contact against a perpendicular simulator, arresting 2 more degrees of freedom.
And finally, the tertiary datum uses 1 point of contact to lock that final translation.
Exactly. Once you have arrested all 6 degrees of freedom using those specific datum features, the part is kinematically locked.
So an inspector in Tokyo and a machinist in Detroit will place that imperfect part into their respective datum simulators and achieve the exact same orientation every single time.
Every single time.
That makes perfect sense for a prismatic part. You know, something essentially blocky or flat where you can easily rest a primary surface against a granite table.
Right. Easy enough.
But the source material also tackles non-prismatic complex geometry. So if a part isn't a perfect cube-like measuring a lucky potato or a giant car door or a warped die-cast transmission housing, how do you put that flat on a surface plate?
You can't. Placing that onto a flat surface plate is entirely useless.
Because of the inherent warp, the part is going to rock back and forth on the granite.
Exactly. A rocking part means unstable, non-repeatable measurements. If the quality inspector pushes down on the left side of the casting to stabilize it, they establish one coordinate system.
Oh, and if the machine is pushed down on the right side during setup, they established a different one.
Yep. You are right back to conflicting results and scrapped parts.
Which is why the standard introduces datum targets.
Yes. Instead of attempting to use the entire uneven surface of a complex part as a datum, the design engineer specifies exact pinpoint locations for the simulators to make contact.
The text shows examples using spherical pins or flat bottom pins of very specific diameters, right?
That's right. By using datum targets, the engineer dictates the exact X, Y, and Z coordinates where those simulator pins must touch the casting.
So the 3-2-1 rule still applies.
It still applies, but instead of resting on a broad, imperfect plane, the transmission housing rests on 3 specific spherical pins for the primary datum, 2 pins for the secondary, and 1 for the tertiary.
Oh, wow. So you mathematically bypass the warp or the complex curvature. By defining the exact coordinate points of contact, the part seats perfectly onto those pins without rocking.
Exactly. It provides absolute stability for parts that are inherently unstable, completely unifying the inspection process regardless of how wonky the overall casting might be.
That is an elegant solution to a very messy physical reality, but stabilizing the part and creating a unified measurement framework is really just the foundational step.
Right. If we connect this to the bigger picture, the true financial leverage of GD&T, how it actively drives down the cost of manufacturing, comes from how the system defines the acceptable limits of the geometry itself.
This brings us to material conditions, and specifically the concept of maximum material condition, or MMC. If we want to understand how GD&T saves a company millions of dollars, we have to look closely at MMC. I want to break down the mechanics of this because it fundamentally changes how tolerances are calculated. Let's look at a really clear real-world visual, like the relationship between an external feature, like a machined pin, and an internal feature, like a drilled bore it needs to slide into.
Okay, so every manufactured feature has a size tolerance. A pin designed to be 1,000 inch diameter might have an allowable size tolerance of plus or minus 0.005 of an inch.
Okay.
That means the pin is legally acceptable as long as its diameter falls anywhere between 0.995 inches and 1.005 inches.
Got it. So maximum material condition refers to the state where the part contains the absolute maximum amount of actual metal permitted by those size limits.
Exactly. So for the external pin, MMC is its largest allowable size, in this case 1.005 inches.
That's the heaviest, thickest pin you can make within the tolerance band.
Yes. And conversely, for an internal feature like a bore or a hole, maximum material condition is the smallest allowable hole.
Right, because a smaller hole means less material was removed, leaving the maximum amount of metal remaining in the surrounding block.
You've got it.
The source outlines rule number 1 of GD&T, which is known as the Taylor principle. It states that when a feature is at its maximum material condition, its form must be perfect.
Right. If that pin is machined to its absolute largest allowable diameter of 1.005 inches, it must be perfectly straight to ensure it will still physically assemble into the smallest allowable bore.
The boundary of perfect form at MMC essentially creates a virtual envelope that the part cannot violate.
Yes. If the pin is at its maximum size and it has even a slight bend or bow, it will breach that envelope and the parts will bind during assembly. They won't fit.
But the reality of machining is that parts rarely come off the line exactly at their maximum size, right?
Yeah.
Tools wear, settings drift, and you usually end up with parts that fall somewhere in the middle of that tolerance band.
Very true.
If MMC means the part is at its maximum allowable metal, then any deviation from MMC means we have a skinnier pin or larger hole. Functionally, that creates extra clearance between the two mating parts.
Which leads directly into the concept of bonus tolerance.
Tell me about bonus tolerance.
Well, in a traditional old-school coordinate drawing, size and geometric shape were treated as entirely separate, rigid boundaries. If a drawing said a pin had a straightness tolerance of 0.002 of an inch, that was the strict limit.
Okay.
If a pin was machined on the skinnier side of its size limit, but had a straightness deviation of 0.003, the inspector would flag it, fail it, and throw it in the scrap bin.
Even though that skinnier pin would have physically fit into the mating hole perfectly fine, because the smaller diameter compensated for the slight bend.
Exactly the problem. The old system threw away perfectly functional components because it couldn't mathematically adapt to the relationship between size and form.
Here's where it gets really interesting. By applying the MMC symbol to a geometric tolerance, the design engineer dynamically links the geometry to the actual produced size of the part.
Yes, exactly.
The system basically says, because you manufactured this pen smaller than its maximum limit, you have created extra clearance. We are going to reward you by reallocating that clearance as bonus geometric tolerance.
It is the core mathematical genius of functional dimensioning. If our pin has a positional tolerance of 0.005 inches at MMC, and the machinist cuts the pin 0.002 inches smaller than its maximum size.
Then that 0.0002 inches of size departure converts directly into bonus positional tolerance.
Right. The pin is now legally allowed 0.0007 inches of positional deviation. The tolerance zone physically expands.
That is a massive philosophical shift. You are moving away from arbitrarily penalizing a geometric deviation, and instead you are validating the functional clearance.
You are telling the manufacturer that as long as the surface of the pin doesn't violate the worst-case boundary of the mating hole, it is a good part.
And the immediate result on the factory floor is that scrap rates plummet. Parts that would have been thrown away under the old rigid coordinate system are now legally accepted because the GD&T framework mathematically proves they will assemble and function correctly.
It's incredible. You save raw material, you save energy, and you save the machine time that went into producing that part.
And the financial benefits compound when you look at how MMC alters the inspection process itself. Because the MMC modifier establishes a fixed worst-case boundary, what GD&T calls the virtual condition, it allows quality control to use functional hard gauging.
Yes, the source material specifically highlights this.
Instead of setting up a complex, time-consuming inspection routine using a coordinate measuring machine, where a probe has to map the entire surface of the pin, calculate the axis, determine the actual local size.
And then run an algorithm to see if the position and size fall within the acceptable variables.
Exactly. Instead of all that, you can just use a go gauge.
Right. A go gauge is a physical block of tool steel that is precision machined to represent the exact virtual condition of the mating part. It simulates the absolute smallest hole located at the extreme edges of its positional tolerance.
So the quality control process for a production run of 10,000 pins becomes incredibly streamlined. The inspector picks up the manufactured pin off the line and physically inserts it into the go gauge.
If the pin goes in, it verifies instantly that the combined effects of the pin's size, its straightness, and its position will not interfere with the mating component.
If it fits, the part is functionally guaranteed to assemble.
It eliminates the complex math and the slow metrology equipment for every single production unit. For high-volume manufacturing, deploying go gauges driven by MMC tolerances drastically reduces the bottleneck of inspection.
Lowering overhead costs significantly while guaranteeing assembly. It is remarkable to trace this evolution. I mean, we started with an industry reliant on coordinate guesswork, where arbitrary centerlines caused argument between engineers and machinists.
And perfectly good parts were scrapped due to ambiguous drawings.
And we transitioned into a highly structured, mathematically rigorous language. The implementation of GD&T replaced that guesswork by forcing engineers to establish undeniable datum reference frames, locking down those 6 degrees of freedom.
It provided the tools to accurately stabilize complex, warped castings using pinpoint datum targets.
And perhaps most critically, through the Taylor principle and the application of maximum material condition, it shifted the focus from arbitrary boundary constraints to actual functional assembly.
It dynamically reallocates tolerances, saves companies unimaginable amounts of money by validating parts through bonus tolerance, and streamlines quality control with functional hard gauging.
It truly is the invisible framework of the modern supply chain. I mean, every reliable, mass-produced item you own, the device you are listening to this on, the vehicle you trust on the highway, the commercial aircraft operating at 40,000 feet,
none of them would be economically viable to produce or physically reliable at scale without GD&T standardizing exactly how their individual components interface.
We open this deep dive by discussing the human expectation that engineered blueprints represent a world of absolute rigid perfection. But peeling back the layers of GD&T reveals something far more sophisticated.
It really does.
This system proves that chasing theoretical perfection on a factory floor is not only physically impossible, it is a fast track to financial ruin. The true genius of modern engineering isn't in demanding a flawless part.
No, not at all.
The genius lies in precisely calculating exactly how imperfect a physical object is allowed to be, while guaranteeing it will still function flawlessly in the real world. It makes you wonder, what other complex systems in our businesses or even our daily lives could benefit from clearly defining our acceptable functional tolerances instead of relentlessly burning resources chasing an impossible perfection? Something to think about.